Hey, we're talking exponential growth and decay right here. So there is a general formula in the textbook that says y equals a times b to the x power. I like cleaning that up in a different way. So y is kind of like our final amount. The a here is the initial amount. It's the amount you start with. And then the number with the exponent, I like to think of it as 100% plus or minus some amount. And then we do it in decimal form to the x power. Now x is like the number of times that happens. A lot of times it's like years, or we'll get into other instances where it's like monthly. So you'd put the number of months there. All right, so let's try this out. Since 1995, the daily cost of patient care in community hospitals in the U.S. has increased about 4% per year. In 1995, such hospital costs were an average of $968 per day. We're going to write a formula for it, like a general equation, and then we're going to evaluate that equation for how many years have passed until 2010. So you can do y equals, we're going to write it as a function. So we're going to say the amount after t years, a of t. Again, if you want to make it y equals, that's fine. So the starting amount, the starting cost in 1995 was $968. And we're going to multiply that by, remember, this number here with the exponent is going to be like 100% plus or minus something. Now it says it's increasing 4% each year. So that would be 100 plus 4, 104%. But we always do the decimal version of that, 1.04, and that will be to the t power. Right? Again, it doesn't matter if you want to use y's and x's, but t is like the number of years that has passed. So here's our general equation. Then it says part B, use your equation to estimate the approximate cost per day in 2010. No, we're not going to use 2010 as the time here, because it wasn't 2010 years. We have to see how many years passed. It started in 95. And we're checking 2010, so how many years have passed? Well, 95 to 2000 was 5 years. 2000 to 2010 was 10 years. 5 plus 10, we're using 15 years here. So we'll say A of 15 equals 968 times 1.04 to the 15th power. Now make sure you're doing your order of operations correctly. You have to do the exponents first. So if I do 1.04 to the 15th power of my calculator, I get 1.800943506, and it rounds it. Right away, we don't need to write that number. We can go ahead and just multiply that by the 968. We get 1743 and some decimals. We're talking money here, so we'll round to the nearest hundredth. So we'll say $1,743.31. Great, that wasn't even that bad. Let's try another one here. Suppose your community has 4512 students this year. Student population is growing 2.5% each year. Write an equation to model this student population, and then what will it be in 3 years? Now, if we are increasing the amount of students, it's growing 2.5%. That would be 100 plus 2.5. So it'd be 102.5%, but we need it in decimal form, which, remember, that moves it 2 places to the left. So we'll be using the decimal 1.025. That'll be the number with the exponent. So we can say, we can use A of t again. We're talking about time here. The starting amount is the 4,512 times, remember, we're using 1.025. That shows a 2.5% increase per year. 1.025, and that'll be to the t power. T is the number of years. And then we have to actually solve it for 3 years. What will the population be after 3 years? Do the exponents first. 1.025 to the third, long decimal, times 4512. Now, we get 4,858.9. You're not going to have 0.9 students, so you would just round this one to the nearest whole, which would be 4,859. So if it's growing, you add it to 100. If it's decreasing in value, you would subtract it. So exponential growth, if it was graphed, would look like this. It's kind of like if they tell you, hey, you know that old penny problem where they're like, would you rather have $1 million now or a penny and I'll double it every day? Because it's getting doubled, it would be like 1 cent the first day, it'd be 2 cents the second day, then 4 cents. So it's not changing by the same amount, it's doubling each time. That's exponential growth. All right, we have this compound interest formula. This one is a little wild. So here's the formula. Balance, and it's very similar to what we just did. But balance equals the principal, which is the amount you put into the account. Then we have 1 plus, that's like our 100%, plus our rate of whatever they're paying us. It's our percentage. We're going to divide it by n, which is going to represent the number of times it's compounded per year. And then the exponent's not just going to be t, it's going to be n times t. Now that looks very complicated. Once you do a couple of them, it's not bad, but maybe we should label this. B is our balance. P is our principal. It's the amount we put into the account. R is the percentage, it's the rate, but we use the decimal version. N is the number of times it's compounded. And then T is the time in years. Great. Again, once you see it worked a couple times, you'll be okay. Suppose your parents deposited $1,500 in an account, paying 3.5% interest compounded annually, once per year. When you were born, find the account balance after 18 years. That was nice of them. Just throwing down 1,500 bills for us. So the starting amount, principal, is 1,500. 1 plus, the rate is 3.5%. In decimal form, that's 0.035. Now, how many times is it compounded per year? Well, it says annually, which means once per year. So the denominator would be a 1. That number also comes up here and gets multiplied by the number of years, which we have 18. Now, there's a lot of 1s in this. If you're multiplying or dividing by 1, it doesn't change it. So if we clean this up a little bit, order of operations, I would divide first. 0.035 divided by 1 is 0.035. Plus 1 would be 1.035. The exponent, 1 times 18, is 18. Now, many calculators, you could put it in exactly like this, and it'll do the order of operations for you. If you're worried about that, do the exponents first, and then multiply by 1,500 at the end. 0.035 to 18. So this one comes out to $2,786.23. Great. There we go. All right. Suppose the interest rate on the account in example 2 was 4% instead of 3.5%. How much would be in the account after 18 years? So the initial amount was 1,500. It would be 1 plus 0.04 divided by 1, which would be 1.04. And then we want to know what that would be in 18 years. So let's So this comes out to $3,038.72. Nice. Got some extra coin there. Almost $300 extra. They're the same. All right. Now we're going to change it from not just once a year. This one is going to be compounded quarterly. Quarters, if you're thinking about quarters, how many quarters in a dollar? 4. So that means 4 times a year, they're going to calculate the interest and put it into the account. So the starting amount is $1,500. We have 1 plus our decimal version of 3.5% was 0.035. But this one isn't compounded once per year, it's 4 times per year. So we're going to put the 4 down there. We're also going to multiply the 4 in the exponent times the time, which we said 18 years earlier. So let's see how this changes stuff. 0.035 divided by 4 plus 1 is 1.00875. 4 times 18 is 72. So if we took that to the 72nd power, we get 1.8724 blah 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 blah. We can multiply that by the 1500. We get $2,808.71 if it rounds. Suppose the account in example 3 paid interest compounded monthly. Whoa, so if it's monthly, how many times a year is that? It's 12. So we would replace these 4s with 12s. Boop. Now I'm just gonna 12 times 18 in my calc is 260. So our exponent is going to end up being 216. So I'm going to do this all in my calculator. I'm not even going to write any more steps, but make sure you do it in the proper order. 0.035 divided by 12 equals plus 1 equals 1.002916666. We're going to take that to the 216th power, and we're going to multiply that by 1,500, and we end up with $2,813.83. All right. Here we go. Part B. You deposit $200 in an account. Okay, so that's our starting amount. We're getting 5%. So 1 plus 0.05, and it says it's compounded monthly. So the 12 goes down there. It also gets multiplied by the time. I'm going to clean up this equation. Since we are going to figure it out for 1 year, 2 years, and 5 years, I'm going to combine what I can. So 0.05 divided by 12 plus 1, we get 1.00416 approximately. And I guess technically it would be 7. So there's a 6 after it. And then we're going to do 12 times the number of years. So for 1 year, 12 times 1 is 1. So let's do this. To the 12th power times $200. So 1 year came out to $210.23. Now if we were to do it for 2 years, let's see, 1.00417. 12 times 2 is 24. Times 200. That comes out to $221.01. And then let's see what it is for 5 years. Now 12 times 5 is 60. So we'll use 60 as the exponent. 1.00417 to the 60th power times 200. $256.72. Woo! Again, it's getting used to the process, putting it correctly into your calculator. Once you figure out kind of the routine of it, it's not bad. The half-life of a radioactive substance is the length of time it takes for one half of the substance to decay into another substance. To treat some forms of cancer, doctors use radioactive iodine. The half-life of iodine-131 is 8 days. A patient receives a 12 millicuries treatment. How much iodine-131 is left in the patient 16 days later? All right, so the starting amount, we're putting in 12 millicuries. Now, if we're talking a half-life, if we're starting at 100%, we're saying we're chopping that in half every half-life. That's 50%, right? 50% in decimal form would just be 0.5. And then it's the number of half-lives. It says it gets cut in half every 8 days. We're wondering, well, how much will there be in 16 days? So how many 8-day cycles happen in 16 days? That would be 2 cycles, 2 half-lives. So that would be our exponent. So 0.5 to the second power is 0.25. 0.25 times 12 is 3. So it comes out to 3 millicuries. Sick. The next one's asking about how much would be in 32 days. So it's still going to be, the starting amount is 12. Still 0.5 because it's half-life. But how many 8-day cycles happen in 32 days? You could just divide them. 32 divided by 8, 4. So there are 4 half-lives here. 0.5 to the fourth, 0.0625 times 12. That's just 0.75 millicuries. Suppose you start with a 50 millicurie sample. How much is left after 1 half-life? What's half of 50? 25. How about 2 half-lives? What's half of 25? 12.5 millicuries. Cesium-137 has a half-life of 30 years. Whoa. Suppose a lab stored a 30 millicurie sample in 1973. How much of that sample will be left in 2003, 2063? So we're starting with 30. We're talking half-life. Now, how many 30-year periods passed from 1973 to 2003? That's 1 30-year period. So that's 1 half-life. So 0.5, half of 30 is just 15. And that's in the year 2003. Now we need to see how many half-lives passed between 1973 and 2063. So if you subtracted 2063 minus 1973, it would tell you that's 90. And the half-life happens every 30. So how many 30s go into 90? 3. So there's going to be 3 half-lives here. 0.5 to the third times 30, 3.75 millicuries. That was in 2063. Man, thank goodness we have calculators. I believe this is the last one before the practice. Since 1980, the number of gallons of whole milk each person in the U.S. drinks each year has decreased 4.1%. It's decreasing. We got to subtract it from 100. 100 minus 4.1 is 95.9%. We always use the decimal version, which would be 0.959. This would be the number with the exponent. Let's see, in 1980, each person drank an average of 16.5 gallons of whole milk per year. Wow. Write an equation to model gallons. All right. Gallons. I'm just going to use A and T again. The amount after T years, the starting amount was 16.5. Our rate of change, remember we subtracted it from 100, got 95.9%. That would be 0.959. And that is to the T power. T is the number of years. Use your equation to find the approximate consumption per person of whole milk in 2000. So if we're starting at 1980, and now we're in the year 2000, that's 20 years. So let's see how much milk they're chugging 20 years later. Put that in my calculator, 16.5 times 0.959 to the 20th. Oh, now they're down to 7.1 gallons. I rounded that off. It's a long decimal. 7.142596023. You know. One more. In 1990, the population of Washington, D.C. was about 604,000 people. That's our initial amount of people. So part A here, it says, well, how much were there initially? 604,000. Since then, the population has decreased about 1.8% per year. The decay factor is that 1.8%. Write an equation to model the population of Washington, D.C. since 1990. Now it's decreasing, so we would have to subtract that from 100. 100 minus 1.8 is 98.2%. In decimal form, that would be, here, I'm going to write the equation. Starting amount, 604,000 people. If we do 100 minus 1.8, we're at 98.2, which is 0.982 to the t power. T is the number of years. Suppose the current trend in population change continues, but predict the population in 2010. So how many years passed from 1990 to 2010? 1990 to 2000 is 10 years. 2000 to 2010 is 10 years, so that would be 20 years. So A of 20. 604,000 times 0.982 to the 20th. Now we're talking the population of people, so we'll just round this to the nearest whole. 604,000 times 0.982 to the 20th power. I got 420,000 and approximately 17 people. DC's gonna empty out soon if that keeps going, man. Come on. I hope you had fun. I'm trying to stop the recording.